In this short lecture video, we will examine the equilibrium constant, something that we have talked about extensively at the start of Chem 124, in terms of the units used in the equilibrium constant. This material is nicely covered in section 14.2 of our Chang textbook, and it's really worth reading through this section and examining the examples there. We will examine the equilibrium for CO plus Cl2 goes to CoCl2. This product is called phosgene and unfortunately is the first chemical agent used in warfare. It was used extensively during World War I and was very detrimental to the lungs of the soldiers who were unfortunate enough to breathe this in. The equilibrium constant will of course be written as concentration of products over concentration of reactants, and in this case the equilibrium constant has a numerical value greater than 1, and so we know to expect more products as the system reaches equilibrium. For gases, however, it is much more common to express the amount of gas in terms of its partial pressure. And so we can write the exact same equilibrium expression using units of partial pressure. So we would have the partial pressure of the products over the partial pressure of the reactants. And these two expressions are exactly the same, except they don't have the same numerical value because the units are different. But we can convert between partial pressure and concentration using the ideal gas law. So the ideal gas law written here, pressure equals NV over RT, is written so that concentration is part of the expression. Moles over volume is concentration. And so for any one partial pressure, the partial pressure can be written in terms of concentration. So the partial pressure of CoCl2 is written as the concentration of CoCl2 times RT. We can now go to the expression for Kp, and everywhere the partial pressure appears, write the expression for partial pressure but in terms of concentration. And so we have Kp is the partial pressure of CoCl2, but this is concentration of CoCl2 times RT, but this is partial pressure, and then divided by partial pressure of CO and partial pressure of. What we see immediately is that RT appears in both the denominator and the numerator, and consequently can be canceled, one in the denominator and one in the numerator, and we're left with an expression that has concentrations of reactants and products and the RT factor that converts from pressure to concentration. But as you will see, what's just been circled is in fact the equilibrium expression in units of concentration, and so Kp can be written in terms of Kc. Here is Kc, and for this reaction divided by RT. Now importantly, this relationship is only true for this reaction or reactions of this type. Let's look at another example of an equilibrium where Kp, the RT term, appears in the numerator and not the denominator. So here's a important chemical equilibrium. This one, the product NO2, is that awful brown color you see in large metropolitan areas with a lot of car exhaust. Los Angeles comes to mind, but that brown smog, the color, it comes from the NO2 molecule. And we'll write the equilibrium expression in terms of first concentration of products squared, because the coefficient 2 appears with NO2, over the concentration of reactants. Now, writing this in terms of partial pressures, which is in fact more common, would be the partial pressure of products squared over the partial pressure of reactants. And we'll do the same thing where I can express the partial pressure of any one species as its concentration times RT. And so we will rewrite Kp, but now plugging in partial pressure of NO2, but in terms of the ideal gas expression of that, concentration of NO2 times RT. And of course both terms are squared because partial pressure of NO2 is squared in the equilibrium expression. And the partial pressure of N2O4 is given in the denominator. Again, you see that RT appears in both numerator and denominator, but this time when we cancel one of the two in the numerator and the only one in the denominator, and so Kp is expressed as Kc. Here is Kc for the reaction, and times RT. So now RT appears in the numerator for this reaction. So in general, in most cases, Kc does not have the same value of Kp, but differs by some factor of RT. The general form of the relationship between Kp and Kc is that Kp equals Kc times RT raised to a power that depends on the number of moles of gas, and so delta N is the change in the number of moles of gas. So delta N is the number of moles of gas that you have as a product minus the number of moles of gas you started with as reactants. In this specific case, we have 2 moles of gas as product minus 1 mole of gas as reactant, and that means the change in number of moles are 1, and so for this case Kp equals Kc times RT to the 1, which is what we got when we canceled RTs. It is true that Kp will equal Kc when the number of moles of gas on the reactant side and the product side are the same, and the change in number of moles of gas is 0. Let's work one last example where we can plug into this new relationship. And so we're going to examine the chemical reaction that produces ammonia, a very important component in making fertilizers and important for feeding our planet. This is an equilibrium that lies way, way, way to the reactant side, and so chemical engineers have to work hard to push this reaction to produce the much needed ammonia. So we want to solve for the Kp for this chemical equilibria, and Kp is always equal to Kc times this factor of RT, and it's RT to the change in number of moles of gas. So on the react, we start with 4 moles of gas, and we only end up on the product side with 2 moles of gas. And so delta N in this case is I end with 2 moles and I start with 4 moles, and so the change in number of moles is -2. And so Kp is the value of Kc, in this case 2.02 times 10 to the -5. And now the choice of R is very important. We choose R so that the partial pressures will be in the units we're interested in. If we want the units to be atmospheres, then we choose R in atmospheres, 0.0821 liters times atmospheres per Kelvin mole. And the temperature of this equilibrium we're examining is 300 Kelvin, and this is all to the -2. And so we have to pull out our calculators and do some math. Examining that gives us Kp is 3.33 times 10 to the -8. This is nearly 1,000 times smaller when we use units of atmospheres than when we use molarity. For the amounts of reactants and products, but if we were to solve a problem using atmospheres, this would be the value that we would have to use for the equilibrium constant. It does have units. The units are atm to the -2, but rarely are those reported. Our textbook never reports them, but you will see researchers who let you know what units they're using for their partial pressures.